Hi, everybody. My name's Ivie Minney, and I go to school at West Virginia State University, and my project was on the synthesis of 2,3-diaminoanthracene. The 2,3-diaminoanthracene is going to be used as a starting material to create an organic ligand that's going to be part of a bimetallic complex, including ruthenium and palladium. This complex is going to be explored as a photoactivated anti-cancer agent. The aim of this project is to reduce the harmful side effects that are present in current cancer treatment. So the problems with current cancer treatment today is that treatments such as radiation therapy, chemotherapy, they all have really nasty side effects that we really want to avoid. So this molecule acts as a really selective treatment where it's photoactivated, so you can shine a light on the cells that you want to treat while the surrounding cells remain healthy and intact. This is the organic ligand that's going to be used. Overall, this was a 5-step reaction, starting with 2-aminoanthraquinone. This was a pretty easy synthesis. The purification methods were pretty simple. Recrystallizations were mostly used. The use of column chromatography was not needed, which was nice, and it really reduced the times needed to purify my product. So my step 1, I started with 2-aminoanthraquinone, reacted it with ethylchloroformate in nitrobenzene at 160 degrees Celsius overnight. And I got anthraquinone 2-urethane at a 94% yield. And I have the mechanism shown here if you want to look at that. My purification methods used was just rinsing it with acetone in a Buchner funnel. And with no further purification, was moved on to the next step. The anthraquinone 2-urethane was reacted with nitric acid and sulfuric acid in an ice bath because the reaction was exothermic. And I got re-nitroanthraquinone 2-urethane at a 50% yield. And again, I have the electrophilic aromatic substitution, the nitration shown in the mechanism here. The purification method used was a recrystallization in nitrobenzene, which I did have some trouble removing that nitrobenzene afterwards because it had a very high boiling point and it just wanted to stick to my product. So I eventually ended up just moving on with the next step, even though there was still a little bit of nitrobenzene on my product. But it did not seem to affect my results. My step 3, I started with the previous product, re-nitroanthraquinone 2-urethane, and I reacted that with sulfuric acid and water. And I heated that at reflux for 3 hours. And I got a 78% yield of the 2-amino-3-anthraquinone. There was no purification step. This was just the crude product was just used into the next step. And again, I have the mechanism shown. My step 4, I started with the 2-amino-3-anthraquinone, reacted that with sodium sulfide and water. I heated that at 90 degrees Celsius for 2 hours, and I got a 67% yield of the 2,3-diaminoanthraquinone. The reaction done was just the reduction of this nitro group into the amine group. And I've included this picture because all of my previous products have been various shades of brown solids, which is nice, but I really liked this product because it was purple, so I decided to include that in my presentation. The purification methods used was to just wash with a lot of cold water and move on to the next step. Here I have my proton NMR of that product. I have the solvent peak and some water here. Down here is the literature values for the product that was given in their procedure. Here, they did theirs in THF while I did mine in acetone, so the peaks are in slightly different places, but they still do correspond with each other. Here I have the amine hydrogens and the aromatic protons over here. My step 5, I started with the 2,3-diaminoanthraquinone and reduced it to the 2,3-diaminoanthracene using zinc activated with copper sulfate in a 5% NaOH solution. And I heated that at 19 hours at 160 degrees Celsius, and I got the lowest yield of 28%. The purification methods used for this step was first an extraction with THF, and then a recrystallization in nitrobenzene, and finally a recrystallization in toluene to further increase purity, which could also lead to the low yields, because many recrystallizations over and over again is going to reduce your yield. But I have not got the chance to increase the scale of this reaction yet, so that might have something to do with my low yields. I had to run this at a small reaction to see if the reaction would actually work. And I have not had the chance to increase the scale just yet. But here's my proton NMR of that small scale reaction. Here's my solvent peak, and again, water. And again, they ran their proton NMR in a different solvent than mine, so the shifts are going to be slightly different, but they still will correspond with each other. Again, here is the nitrogen or the amine protons and the aromatic protons over here. And I have not had the chance to run a carbon NMR to confirm this proton NMR. We have had some delays with our NMR here, but that will be included in my future work. In conclusion, I have up to my step 5 completed at a small scale reaction. I will increase the scale of my reaction in the future. This 5-step synthesis had overall high yields. My lowest yield was 28%, but the rest of them were all 50% and above. I really liked this procedure used because it did not require the use of column chromatography for separation. I only used recrystallizations and rinses and extractions, which was very helpful, and so it drastically reduced the amount of time it took to purify my product. So in the future, I will scale up the step 5 reaction. I will get a carbon NMR of my final product. And then once that's all done and I have enough product, we can move on with the next step in forming that organic ligand. And then further on, reacting those with the metals to form that bimetallic complex. And then eventually it will be able to be explored as an anti-cancer agent. Here are my references and my acknowledgements. I'd like to thank West Virginia State, of course, for letting me use their facilities and giving me the great opportunity to do research at the school. I'd also like to thank McNair for funding this semester's of my research. And of course, I had the Science and Research, West Virginia Science and Research funding my summer research program, which I worked on this project as well. I'd also like to thank all my lab mates because they have been a wonderful help teaching me how to use the different instruments and getting me acquainted with the lab in general. So thank you for watching, and if you have any questions, I'd be happy to answer. Thank you.